So I'm happy to introduce now Mustafa Duya from the company FEV. He has studied mechanical engineering a few days ago and at East Western University based in Ankara. Then he has worked for a few years, for 10 years at Ricardo Company in the UK. And now he is with FEV company in Aachen, Germany. And he is prepared preparation for today about electric powertrain NVH analysis in hybrid and electric vehicles. Welcome, Mustafa.
Yeah, thank you for the introduction. So when the agenda of the conference was initially introduced, I was the last presenter before the lunch. Thank you for PowerSys marketing team. Now I'm not. So I'm not the only obstacle before lunch, but there is one more. So Samba-san will share being obstacle with me before the lunch, but no worries. I'll try to make it quick and painless. Do you know how many cars are there in the world today? Any guess? It's a little bit more than that. So it is almost 1.5 billion cars running on the roads today. And I have good news for electrical engineers, for JSOL, for PowerSys. That will come in a minute. Today, only 1% of those cars are electric, but it will increase. If you look at the sales, worldwide sales last year, it was 66.7 million, and 10% of those cars were battery electric vehicles. And any guess what will be the worldwide sales in 2040? There will be right. But what we project as FEV, there will be 119 million cars sold in 2040. And 68% of them will be pure electric. So good news for PowerSys, good news for JSOL. There will be a lot of opportunities for you. So I said this was our projection. So who we are, who is FEV? So we provide future mobility solutions for our partners, our customers all around the world. We are headquartered in Aachen, Germany. That's the place where I am based. But we have more than 40 offices in 5 continents distributed around the globe. And we have more than 7,000 employees. Most of them are experienced engineers. And what we do, we develop mobility technologies, mobility solutions. So from blank sheet, we develop vehicles, we develop powertrain and electrification, intelligent mobility, energy, software and testing solutions, and we do consulting. So after this bit of introduction, let me come to the point of today's topic. A little bit further introduction. So there are major key differences between conventional internal combustion engine vehicles and battery electric vehicles. So for the IC powered engines, most of the noise is coming from powertrain, then road, wind, and auxiliaries come. Whereas for battery electric vehicle, the noise are dominated by road and wind, then powertrain and auxiliaries come. And there are a number of different development fields. So the road noise is tried to be reduced, wind noise development as well. Then electric powertrain noise is less than internal combustion engine, but it's a little bit more annoying with tonal character. Then active sound control, as well as the contradictory situation between weight reduction and NVH issues. But among all these, what we are focusing today is this electric powertrain noise. And for electric powertrain NVH simulation, we do different analysis in different phases of the development. Concept design, domain design, and then system design. In system design, there are different methods that we use, FEA, BAE, and then also multi-body dynamics. That's what I am going to focus on today. So virtual dynamics is our commercial software for mechanical dynamic analysis. And this system level development includes flexible housing and stator, gear stiffness calculation for rattle and whine problems from the gearbox, dyno control speeds, flexible drive shafts, and electric powertrain mount stiffness and loss are coming from measurements. And we calculate individual tooth forces, which are more interesting for you, I believe. And we use analytical or FE model coupling between interacting bodies. And we have either flexible or rigid components like shafts, rotors. And then we have different fidelity level bearing models. So if you look at the workflow of how we do this, we have a seamless integration of different software, which is orchestrated by virtual dynamics for mechanical dynamics. Then we take into account structural dynamics from the FE models to calculate the vibrations of the surface of the powertrain. And then electromagnetic forces come in place with JMAG. And then with the help of all these software, we also calculate the acoustic radiation using Actron. Or if we are not acoustic experts, we provide a seamless integration to Actron. Actron solver runs behind the scenes. You don't need to be an acoustic expert. All the necessary important results are written, including audible wave files that you can subjectively assess the sound quality. So what is done with JMAG? We calculate the individual tooth forces at the stator. And the challenges are reaching the steady state that requires many electric cycles, and especially at high RPMs. And this problem is also require small time steps, and we are talking about multi-operating points, different loads and different revolutional speed conditions. So the solution is JMAG RT that was presented earlier today. So probably I am the least knowledgeable guy in this room about JMAG RT. You probably all know this. So it enables model-based development with high accuracy, allows plant and control designs to be performed concurrently. And it has a system to generate high fidelity plant models in a system level. And there are a wide range of applications. For this particular case, there are two options. One is RT in control circuit model. The other one is in JMAG designer. So in control circuit, the starting point is a FE model with the sinusoidal current that creates a plant model and lookup tables that we can select the operational point. And then this in the control circuit, there is the RT model that creates the current waveform with high harmonics that speeds up the simulation a lot. And then we can we reach the steady state, we do the FE model simulation with high harmonics, and we calculate the electromagnetic forces. And this approach was also validated with the measurements. The current waveforms compared with the measured ones, and higher harmonics are reproduced. So magenta is measured on this test bench, and blue, dark blue is the calculated. Pretty good match. So in JMAG, there is a pre-installed script, so-called NVH force export. So at each stator tooth, the radial and tangential forces are written in a CSV file, and we import it from the CSV file into virtual dynamics environment. So use cases, electric powertrain. Yeah, this is a 2-speed electric powertrain. Depending on the power flow between these two different planetary sets, the speed is decided. Here are the torque and electromagnetic forces coming from JMAG that feds into virtual dynamics for mechanical dynamics simulation. And with the participation factor, we calculate the radiated noise. And this particular model, we have flexible electric motor housing, flexible gearbox housing, flexible shafts, radial and tangential forces at each stator tooth, revenue planetary gear set, and detailed gear contact model with calculated gear stiffnesses on the fly, and higher fidelity roller bearings. Yeah, this is the electric motor, rotor torque, time domain simulation, and the radial and tangential forces. You can see the vibrations on the housing that will eventually create a noise. These plots are the forces between different gear sets. We run a speed ramp-up simulation starting from 3,500 RPM to 7,500 RPM in 2 seconds. And we also see a sine chain on the gear pair forces, which means there is a potential for rattling noise. So in the standard, ISO standard, there are defined microphone locations that we predict the acoustic radiation. And on one of the microphones, we see this Campbell diagram. Yeah, prominent orders visible in the lower frequency band, and there are also higher group of orders in the relatively higher frequency band. If we try to understand where these orders are coming from, we look at the electric motor torque in time domain, apply Fourier transform, and we see they are actually, these orders are coming from electric motor rotor torque. Similarly, if we take a single radial force at the stator tooth and apply Fourier transform again, we see that these orders are coming from the radial force ripples. Equally, if we sum up the radial forces and then apply FFT, the total radial force orders are appearing on this Campbell diagram. So in summary, we try to understand where these orders are coming from: electric motor torque, single tooth radial force, and total radial force. And there is an indication of minor gear rattle at this frequency band here. So we also can identify the major eigenmodes that are contributing to the noise. Yeah, the eigenmode 6 up until 30. Some of them are listed here, which are the major ones, basically coming from the electric motor housing. And this plot shows one of the microphones element contribution to the noise. And we can also hear the noise. We could hear. Can anybody help me to hear this noise? I think it's muted. Yeah, that's the typical tonal character of an electric powertrain. So by looking at the automatically generated Campbell diagrams, we can assess quantitatively the NVH behavior of the electric powertrain, but equally, we can also assess it subjectively, like listening and trying to qualify whether this sound is good or bad, or take some other measures. I have another example, which is a P2 topology hybrid powertrain. So depending on where the electric motor is on the vehicle along the driveline, the hybrid topologies are defined from P0 to P4. So this is an inline four-cylinder internal combustion engine mounted to through a dual mass flywheel to a transmission, manual transmission, and then there is an electric motor mounted to manual transmission. We have an accelerometer on the transmission casing. We have flexible bodies so that we can predict the vibration of the casing. And at this accelerometer location, we predict the acceleration of this powertrain. And equally, on the test bench, we measure the acceleration by using an accelerator on the bench. And also we have a microphone that we also measure the radiated noise. This is a microphone measurement, accelerometer measurement, and this is the virtual accelerometer result out of virtual dynamics prediction in this workflow. So if we compare the measurement and prediction, we managed to capture the major orders of the frequencies as well as the amplitude of the accelerations. It's pretty good correlation. And this is only possible because the coupled simulation of engine, transmission, and electric motor are done with virtual dynamics. So in summary, I tried to show a workflow in which you can predict the NVH behavior of an electric powertrain. You don't need to be an acoustic expert. All the relevant important plots and sound files are written automatically. I hope I promised my word and finished fast and painless.
It was painless and very interesting. Thank you very much, Mustafa. And I think you will have some questions or comments.
Yeah, thank you very much for nice presentation. A question about magnetic part. You used lumped force and stator tests, right?
Correct, yeah.
And have you compared it with the nodal force and the whole stator to see the difference between the result of acceleration?
So what we do is we calculate the lumped force, as you said, but if you have some FEA background, so we use RBE3 element on the stator tooth to distribute that force to the entire stator tooth. But we haven't tried just the distributed coming out of electromagnetic analysis, no.
Okay, thank you.
Just in short, you said it's a software package where you don't need to be an expert on acoustics so they can use it. My experience is when we have somebody who is working with a very good program, but himself is not expert on that, there can be still major errors if you handle such a complicated system as it is in total, if you don't handle it in the right way. So my question is it really the way that you can say you don't need to be an expert and it works safely and you get the physical meanings, results? So is there a lot of things you still have to know? Otherwise, even this program will give you results which are not reliable.
Yeah, thank you for the question. Yeah, of course, you need to have some experience and you need to have your engineering judgment based on your experience and knowledge. What I am trying to say is you don't need to be expert on the acoustic side and what results I need to create. You don't need to worry about this. So this workflow runs the acoustic solver Actron behind the scenes, and the results are automatically generated based on the acoustic experts' judgment that which results are relevant for this particular case. That's what I am trying to say. Yeah.
Thank you. Okay, I think there are not any more questions, and I think we are really on time. So perfect. So thank you again for this presentation.
My pleasure.